Hello again. The last few videos, I felt like a chameleon, gray shirt against gray wall. So I moved a little. Anyway, the actually important thing, I've promised you that substitution is important, but I've also stressed that it's really delicate because you need the derivative of the inside function. Um, the way we sort of harmonize those statements well, there are two ways. First, substitution is delicate, but we can deal with unwanted or missing constants. Second, a lot of applications of substitution are really just simple applications dealing with simple functions. I mean, let me give you an example. Suppose we want to integrate e to the x. No muss, no fuss, no substitution. The integral of e to the x is e to the x plus c. Now suppose I want to integrate 2 to the x. Now, this is not an integral we've learned, but something I did tell you is that any exponential function can be rewritten to have e as its base, using the fact that 2 can be rewritten as e to the natural log of 2. 2 to the x is e to the ln 2 raised to the x is the integral of e to the natural log of 2 times x dx. Okay, so we've gotten the exponential, but we've gotten the we've gotten the exponential we're used to working with. But the trade-off we had to make to get e as our base is that now we have a little composition. We don't just have e, we've got e with an inside function here. Our inside function is the natural log of 2 times x. So can we integrate this? Well, we don't, as I've said before, we don't have like an integral version of the chain rule. There's no one size fits all way of dealing with compositions. The only method that we know is substitution. And if we did a substitution, and let u be the natural log of 2 times x. Don't get intimidated or confused. The natural log of 2 is just a number. So when we do substitution du, The derivative of a number times x is the number, and du is the natural log of 2 dx. Only we don't have the natural log of 2 in front of e. We don't have anything in front of e. So does that mean that our substitution has just failed and we can't integrate? It does not. This is what I'm talking about when I say we can deal with missing constants. And the way I approach this is a little different from the way the textbook approaches it. But that's fine. You can, in fact, you are supposed to be reading the textbook. It won't do you any harm to see a slightly different version of the same thing. We've got this function we want to integrate, e ln 2 x dx. And we've had the idea of using u substitution, but the problem is that we don't have the derivative in front of the function. Well, for constants, we can do the following. I want the natural log of u. I don't have the natural log of u. I should have left myself more space, but I am going to resolve this by throwing a natural log of 2 right in there. And you're probably saying, you cannot do this. You cannot just change the integrand and put something in there just because you want it to be there. And of course, you're exactly right. At the same time that I multiply in this natural log of 2, I am also going to divide by the natural log of 2. So do we see that we haven't changed this integrand? I've I have taken this exponential function and I've multiplied it by 1. I haven't changed it, but I've written 1 in this very specific way. I've written 1 as the natural log of 2 times 1 over the natural log of 2. And now 1 over the natural log of 2 is a constant. And I can take a constant and I can pull it right out of the integral. And now we have the natural log of 2 times e to the natural log of 2 x dx. And suddenly I have exactly what I need for this substitution to go through. E to the ln of 2x, that's e to the u. The natural log of 2 and the dx give me the du. Outside the integral, I have this 1 over the natural log of 2, and I can integrate. The integral of e to the u du is e to the u. With our constant of integration. And now u is this, the natural log of 2 times x. So I can rewrite this as 1 over the natural log of 2 times e to the ln2 times x plus a constant of integration. Again, a constant times a constant of integration is still just a constant of integration. And if I were so inclined, I could then recognize that this e ln2 times x is 2 to the power of x. And this integral I found is 1 over the natural log of 2 times 2 to the x plus a constant of integration. But the important thing here is that we were able to deal with a missing constant. And this little u substitution where we want to integrate e raised to a constant times x. This shows up all the time. And it justifies calling the fact that u substitution is able to handle this integral, justifies calling it important all by itself, even if this were the only application, which of course it isn't. As I end this video, I'll just emphasize the fact that we were off by a constant was essential to this going through. Suppose we had e to the 5x, but we had, an x squared in front of it. The integral of x squared e to the 5x. The trick or maybe let's look at e to the x squared dx. The trick I just presented you is not going to work here. If we let u be x squared, then du is 2x dx. And the fact that we're missing a 2 is fine. But the fact that we don't have this x is fatal. Because if we tried to use the trick we just used, where we put the 2x in, but we also divide by it, well, what was the very next thing I did in this example? The very next thing I did after throwing in the missing quantity and then dividing by it was that I pulled the 1 over ln2 out of the integral. And I could only do that because 1 over ln2 is a constant. Now I have a 1 over x, and I cannot pull the 1 over x out of the integral. So if I try to proceed, I wind up with the integral of 1 over 2x e to the u du. And now I'm buffaloed. I managed to turn the dx into a du, but now we've got 2 variables floating around in this integral, and I'm not able to proceed. So this trick only works when you're missing a constant. It is not, sadly, a general fix for you substitution.